Okay, next we're going to look at the comparison theorem for improper integrals, which I'm going to abbreviate CT from now on. And it says that f and g are continuous functions with f of x always being greater or equal to g of x. This upside down a means for all x greater or equal to a. In other words, f of x is always bigger, taller, higher, however you want to think of it, than g of x. So if that is the case, two things can be established. If the integral from a to infinity of f of x dx converges, then the integral from a to infinity of, that actually should say g, then the integral from a to infinity of g of x dx should also converge. So here's picture-wise what you can think of. We're looking at the integral from a to infinity of f of x and g of x. So remember we said that f of x is always bigger or equal to g of x. So we imagine f of x to be higher than g of x all the time from a on. And it says that if f of x dx converges, then g of x basically has no choice but also to converge, which makes sense because if the higher guy, if this region is convergent under f, then it makes sense that the lower function under g from a to infinity should also be convergent. So if the bigger area is convergent, then clearly the smaller one has to be convergent also. Or we could sort of think of it the other way. We can say that if the integral from a to infinity of g of x dx diverges, then the integral from a to infinity of f of x dx also diverges. So why does that make sense? If we think about it and we look at this piece that says that area from a to infinity under g is divergent, meaning under g from a to infinity I get something that is infinite, the limit doesn't exist. Well, if the smaller region diverges, then it makes sense that the bigger region would also have to diverge because it's even bigger than this guy. So they're kind of related ideas. I don't want you to memorize things too much. I want you to think f is always bigger than g. If the smaller one, or I'm sorry, if the bigger one converges, well then the smaller one will also have to converge logically. Or if the smaller one diverges, well then clearly the even bigger one would also have to diverge. That's all the comparison theorem says, and it helps us analyze improper integrals that we may not be able to really do by hand, but compare them to something that we know some information about. So compare them to simpler functions. Let's go look at some examples. So let's determine if the improper integral converges or diverges. So clearly this is shouting out I'm improper because I see an infinity there. So it's a type 1, not a type 2. And I can try to integrate this, but there's a lot of busy stuff going on and I don't really want to bother trying a u-sub or doing it by parts or anything. If all I'm supposed to answer is whether it converges or diverges and I'm not asked to give me what it converges to, then it might be an indication that, okay, I'm just going to maybe use a comparison theorem and make a conclusion and be done with it. Because it didn't say anything about evaluate the integral if it's convergent and tell us what it goes to. So let's look at trying to compare this guy that looks kind of busy to a function that we might be able to know some stuff about already and that might be simpler. And often we think of the little tool that we talked about earlier. These guys end up being really nice for the comparison theorem because we already have some things established for them. We know that if p is bigger than 1, it's automatically convergent. It's a simple function to compare things to. And if p is less than or equal to 1, that it's divergent. And since I see something like a 1 over x in this function, I'm leaning towards maybe I can use that. So let's see how I can simplify this to maybe compare it to this guy somehow. So I'm thinking if I just eat up the e to the negative x part and instead let's look at just 2 to the x. And why did I choose that? Because I thought, well, 2 over x. 2 over x kind of looks like this 1 over x to the p function that I could possibly use. So I just completely got rid of that part. But now I have to do a comparison between what I made up, a simpler function, and this guy that I was supposed to originally analyze. So I'm just pulling out the function and making a comparison between that function and another simpler function that I'm sort of familiar with and might cheat and use this result. So, well, if I'm looking at these two and I'm trying to make a comparison, it's really dealing with inequalities when you do the comparison test. Which one is bigger? Is this one bigger or is this one bigger? Well, if I think about it, e to the negative x from 1 to infinity is always a little positive number. So I'm taking a positive number and adding it to 2, meaning I'm making this numerator bigger than this numerator. Well, if this numerator is bigger than this other numerator, wouldn't it make sense that this guy on the right would always be bigger? So I just established an inequality between what I originally had and what I made up to be a simpler function that might relate to it. And again, my analysis is I'm adding a little piece of positive value to 2, and it's always in the numerator. If I'm adding it to the numerator, well, then I'm making this side be bigger than this side, because it's something bigger divided by the same thing that this guy was divided by. So now I'm thinking, well, I can analyze this as pull out a 2, look at its integral from 1 to infinity of just 1 over x dx. I can look at this integral with the 2 pulled out, and this takes me back to this guy that we sometimes call the p-test. And I know that based on this p-test, let's call it, if p is 1 or less than 1, this is going to be divergent. We know that result from before already. So this guy is divergent, and this guy is smaller than this guy, remember? So if this guy is smaller than this guy, then if the smaller one diverges, the bigger one also has to diverge. So this inequality that I established actually helped me out. If I had compared it to another type of function where an inequality facing the other way was established, it wouldn't be useful, because if the big one diverges, I don't know what will happen to the small one. So now I can say, since this guy, 2 plus e to the negative x over x is always greater or equal to 2 over x on this interval 1 to infinity, we must have, so I want to make a formal conclusion, that from 1 to infinity of what I was looking at diverges by CT, and that's good enough. We know that you mean comparison theorem. So smaller guy diverged, bigger guy has no choice but to diverge also. It's basically this case. The smaller guy diverged, and the bigger one is also going to be divergent. And the key thing was, compare what you started with to a simple function that you already know information about. So let's go look at our function and see what happens. Graphically, let's see what happens with this guy from 1 to infinity and how that relates to the other guy, if things are looking okay or not. So from 1 to infinity, let's zoom out a little bit maybe. Do a regular zoom. Okay, we're only interested from 1 to infinity. From 1 to infinity, this guy looks to be decreasing, and supposedly that guy is going to be higher than this guy that's diverging. So let's go put 2 over x and see what happens. Okay, so 2 over x, the simpler one, has a branch there and a branch there that's actually hard to see unless I zoom in, or you have the TIs that have the different colors that show you what happens. So let's go zoom in a little bit on the right, move to the right to look at things from 1 to infinity. Remember, the first one was the complicated function, there it is. And then the second one, right below it, is the simpler function we looked at. So notice the simpler function always remains below the complicated looking function. And if the simpler one that we looked at diverges, then the other one is always higher than it, so that also must diverge. So graphically things make sense too. So again, we're going to try to determine if this thing converges or diverges, and we're going to compare it to something that's simpler and we know some information about. So this again looks like one of those p-test functions, 1 over x to the p. This -1 in the denominator is kind of throwing things off a little bit, so let me just compare it to the simpler function that I'm thinking of. So this kind of reminded me of 1 over x to the p, but there was that -1 that I kind of ate up because I want to make it look simpler. So I ate the -1, now I'm going to compare the simpler one to the one that I originally had. Now notice on the left, you have a smaller denominator because you're subtracting 1 from whatever that x value is, and we're looking at 8 on to infinity, it looks like. So let's make a note of that. So since I am subtracting 1 from the denominator, and the denominator is becoming smaller, it's 1 divided by something smaller versus 1 divided by something that was a little bit bigger by 1. So you're dividing 1 by something smaller, and so clearly this side has to be bigger because you're dividing by something smaller than you had before. This is the hardest part for the comparison because you have to come up with a function that nicely relates to the other one and then do the analysis of which one is bigger, which one is smaller. And I always say eat up certain parts of the complicated looking function and then just analyze whether denominators are getting bigger or smaller. That might be easier to work with. So smaller denominator means this side must be a bigger number because it's 1 divided by something smaller. And we also know that this looks like one of those p-test business integrals, and we always looked at them from 1 to infinity, but from 8 to infinity it should still hold from a finite number to infinity. So since this has a p-value less than or equal to 1, it must be divergent. So this simpler one that I made up is divergent, and if the smaller is divergent, the bigger one has to be divergent also by the same analysis as before. So we formally write, we say, well, since this complicated function was bigger or equal to the simpler one on the interval of interest, and we already know and we have that that integral is going to be higher and bigger than this simpler integral, and this guy therefore must also diverge by the comparison theorem. So once we make this comparison, we want to formally apply the comparison theorem and say that if the smaller guy basically we know diverged, then the bigger guy also has to diverge, and we must quote what we did was the comparison theorem here. Let's look at one more example. This looks rather complicated. Dealing with by parts and such, forget that. Let's just try to do a comparison and determine whether it converges or diverges. So we know sine of x is trapped between -1 and 1, but if I'm dealing with all positive values in absolute value, then it must be trapped between all positive values 0 to 1. So that's the first statement that must be true. Again, because it's an absolute value, it's between 0 and 1 as opposed to -1 to 1. Then let's multiply everybody by a positive term, e to the -x. So the inequalities don't switch because e to the -x is always positive on that interval, and for any interval that is, and this remains 0. This gives me the new thing I was interested in, and 1 times e to the -x is this. So now, notice we've established a comparison between the complicated function and a simple one that we found. So let's go analyze the simple one. Let's see what happens from 0 to infinity with the simpler function that we know is always higher than this complicated one. Let's just do a quick integral there, improper. So e to the -x is just e to the -x divided by a -1 with a quick use up from 0 to t. T goes to infinity. Remember, the trouble point was infinity, so I replaced it with t. So this guy is just positive, I guess, e to the 0, which is 1. And all I'm worried about is -1 over e to the t and what will happen when t goes to infinity. So this is a -1 over e to the t because that was a negative exponent. Negative and negative, e to the 0 is just 1. So it looks like this guy goes to 0 because I'm dividing by e to the big, and this approaches 1. So it's a convergent integral. And since this is convergent and this complicated is always smaller than it, this also must converge. So let's go write it formally. Since the original function is always less than the simpler one I came up with on the interval of interest, and the simpler one converges, we must also have that the complicated one that's always less than it converges by comparison theorem.